Okay, good morning everybody. Still in the middle of Act 2 here with our exponential and logarithmic functions. Now we're going to focus on the big one here, 7-5. Now we've used all these logarithm properties, and what we're going to do with these is we're now going to put them to good use and actually finally solve exponential equations and logarithmic equations. Let's first start off by taking a look at this. Take a look at this problem, see if you can figure out how to figure out what x is. We've got something going for us here, right? And what is that? Is that we have 7 as the base for on both sides of the equation. If 7 is the base there, and if these two powers here have the same base, then what's that tell us about those exponents there? Those exponents there have to be equal, right? So in order to solve for x, all we have to do is, if the bases are the same, just set the exponents equal to each other, and then we can solve that problem for x. Right? Just a two-step problem there. Subtract the 1 divided by 2. How about this problem? Same situation, right? Because they both have the same base of 11, that means that 3x plus 4 must be equal to 16, so then we can just solve that problem. Subtract the 4 from the 16, so it gives you 12. 12 divided by 3 would give you 4, so I'm pretty sure x would have to be 4. So here I'm going to throw a couple of if-then statements at you. What if A was the same number as B? If A was the same as B, then is this true? Is 2 times A the same as 2 times B? Yeah. In other words, if we multiply both sides by 2, we're going to get the same amount. How about now? Are A and B, is this statement true? A minus 2.4 is equal to B minus 2.4. Should be the same, right? Because we're doing the same operation to both sides, we're still going to get the same result, right? This is just Algebra 101. So why am I showing you all this? Well, what I'm trying to show you as a good move to use algebraically is sometimes it's going to be better to take the log of both sides of the equation. Let me show you how this works. If we have this equation here, 3 to the x equals 17, obviously x needs to be some sort of a decimal, right? Because we know that if we take 3 and square it, that's 9. If we take 3 and cube it, we get 27, so 17 is between there. So just ballparking this number, we're looking for a number between 2 and 3, right? So here's how we get it. What we're going to do here, in order to solve algebra problems where x is the exponent, we are going to take a logarithm of both sides. We're going to take the log of 3 to the x, and we're going to take a log of 17. Here's what this creates for us. This creates a situation where now we can use that plug property, right? Over here, when we have the log of 3 to the x, it's like having this situation here, and we can take that variable p and put it out in front to create this expression right here. So now that variable of x can go right out in front there. So now that we have x times the log of 3 equals the log of 17, remember the log of 3 is just a decimal. Remember, that's just saying 10 to what power is 3, which is going to be a decimal. So if we have a number times x to solve for x, we're just going to divide both sides by that log of 3. Note what happens here. The log of 3 divided by the log of 3 is no different than any other numbers. You're going to get 1. Notice what happens on the other side. The log of 17 divided by the log of 3 is going to give us 2.579 approximately. And so there we go. We've just solved for x, which is the number that we predicted it was going to be, somewhere between 2 and 3. Let's see this again with a couple more examples. How about this one? 5 raised to the x minus 2 power is 200. A thing to look for that would be a dead giveaway to take a log of both sides, as you see here, is notice that with this problem, there's a exponent on one side with a variable of x, The variable x is only used as an exponent on the left side. It's not used on the right side. When that's the case, we can take a log of both sides. Let's use our plug property again. This time, what moves out in front? What's playing the role of p here? It's that entire x minus 2. So we're going to move that out in front. Now just like earlier we divided by the log of 3, now we're going to divide both sides by the log of 5. That's going to divide out to be 1. And we'll be left with x minus 2 equals a log of 200 divided by a log of 5. Now log of 200 divided by a log of 5 will give you a decimal that's pretty lengthy. I'd like you guys to hold off on rounding your numbers until you get your final answer for x. So in order to hold off and get a more accurate answer, maybe the first thing we should try to do is maybe let's add 2 to both sides and create a situation that looks like this. Now let's throw this in the calculator. Let's divide this first in our calculators, giving us that long decimal right there. And then rather than rounding it and adding 2, keep the exact same answer and then add 2. That'll give you a more accurate answer right there. So one other thing you noticed on the last problem I had the rounded to 3 decimal places. I'd like you to round these logarithmic solutions here to 3 decimal places if you would. So approximately 5.292. Notice it's not too hard to check our answers either. Just take that same number, and if you did all the work and had that answer in there, just take 5, raise it to the previous answer, and subtract 2, and sure enough, look at that, we get 200. So what I'd like you guys to do is I want to give you a few minutes to work on these problems here. Why don't you give them about, give them a good 7 minutes on these problems. 7 minutes, and then just pause the video, and then at 7 minutes just restart it again. Okay, so hopefully they paused it so you had some time to work. Let's take a look at these 3 solutions. Did you get these as your answers? No? Well, maybe we can go back and check them a little bit. Let's go back to this one over here. If we're looking at 1a, this is all set up for us to take a log of both sides, right? So let's go ahead and do that. We're going to do the log of 3 raised to 2x equals the log of 27. What's the plug property tell us? Plug property tells us now this 2x can go wee, boop, right out there in front. And so then once we have that, now we can divide both sides by the log of 3. So once that cancels out, now we have 2x being equal to the log of 27 divided by the log of 3. There we go. So according to that, it tells us that we have a 3 right here. And so then to solve for x, we have to divide by 2. And so then x is going to be equal to 1.5. Okay? So there we have it. Notice with those other ones there, you're going to have approximate answers. So once again, just round those to the 3 decimal places.
Cool tricks! Cool tricks!
Whoa! What was that? What was that? Huh, cool tricks, huh? So what kind of cool tricks can we use with this kind of problem here? Let me show you that cool trick we can do here. So with your graphing calculator, and I want to focus on 1b there. I'm going to show you another way you can get that negative 1.565. Go ahead and with each one of those sides of the equation there, 7 to the negative x, put that into the calculator on one of your equation lines. Then put 21 on the other end for y2. Once you have that, go ahead and hit the graph button. Actually, before you do the graph button, strike that. Go to your window key. Because we need a maximum here, where we're looking at a line of y equals 21, your normal viewing window is actually going to be going from negative 10 to 10. I'd like you to change that and change your y maximum, change it to 30 for me. If you just change that y maximum to 30 and then hit graph, now you'll be able to see exactly where that intersection point was. Do you remember how we can calculate an intersection point using these calculators? Yeah, press second and then hit trace, second trace, to get to this calculate menu. And then yup, we want intersection. So do intersection. I believe you can just hit enter 3 times after that, or just answer the questions if you forgot how it goes through. And there we go, we have our intersection point. And notice that right there. Cool. Maybe that's why they call it Cool Tricks, because it is kind of cool. Alright, take a look at this example. 8 raised to the x equals 2 raised to the x plus 6. Let's compare that to the previous problems we've been working on here. Do you notice what's different about this problem? Yeah, notice with this problem here on the left, we have the variable x is used on both sides, the left side and the right side. Notice with all the previous problems we've been doing and the examples that you're working on, the unknown was only on one side of the equation. That made it awesome for taking a logarithm both sides. When you're looking at this problem here with 8 to the x equals 2 raised to the x plus 6, you can still take a logarithm on both sides. But the nice thing about these ones is that there's a couple other ways you can do this problem. Let's look at the long route here. I believe this is the longest way to do it. So let's get this one out of the way. Notice you can do the same thing, take a logarithm on both sides. Notice when you do the plug property though, the x moves out in front and the x plus 6 also moves out in front. So when those move, you're going to have something that looks like this, right? Now earlier, when we only had to move one thing out in front, it was pretty clear which direction we divide our logs. Now that we have variables on both sides of the equation, it's a little bit tougher for us to nail down which way to go with dividing the logs. So let's move like that chess player, let's move that piece, and let's just look at both situations here. On one hand, I can divide both sides by the log of 2, which would get them to cancel out over here, and I have the log of 8 divided by the log of 2. Or, I could divide both sides by the log of 8. But let's move that piece and see if we like what we see. What is the log of 8s and the log of 8s, those are going to cancel out. You take the log of 2 divided by the log of 8, what's that going to give us? It's going to give us 1/3. I have to take 1/3 and move it in there to the x plus 6. Okay, I suppose. But if we go back and look at the log of 2 dividing by the log of 2 on both sides, notice this one gives me 3 and not 1/3. I might like it to go this way. So suppose we did go that way. We cancel this out. Over here we end up with 3 times x, so that means we have 3x there. Hey, I think I know how to finish this problem. Can we just subtract the x from both sides, calling that 2x equals 6? And then we can divide both sides by 2 and then we get 3. And then we can check our answers here, right? If we check our answers and put 3 in for x and 3 in for the x plus 6 power, notice how this pans out. 8 to the 3rd, this is actually 2 to the 9th. Notice in both cases we get 5/12. If you got the same number, that means it worked. So x equals 3 is the correct answer.
Cool tricks, cool tricks!
Hey, it's that guy again. Cool tricks, cool tricks. Will the graphing move work here? Put both sides in and hit graph. Wait a second. That's right, we aren't supposed to get a horizontal line this time, right? We're supposed to get 2 exponential growth curves because both those numbers are greater than 1. So, where do they cross? I wonder if our intersection trick will still work here. So, let's try it. Intersection with those 2 graphs. Enter, enter, enter. And look at that. We got 5/12, but notice, remember, we're after x here, and look at that. X equals 3. Hooray for us. That can work.
Cool tricks, cool tricks!
Oh, I thought I was done with this guy. Hey, there's another way we can do this. Hey, recall this. If we had the same bases here, doesn't that mean that these 2 things have to be equal? Well, can we say the same thing about these right now? No, this says 8 and this says 2. So we can't say that x equals x plus 6. But is there a way to change 8 so that way it's also saying 2 to some power to give us 8? 2 to what power would give us 8? Yep, 3. So if we write this as 2 to the 3rd raised to the x equals 2 to the x plus 6, no harm, no foul. This is still saying 8x. 8 to the x. Now, how about we use our power property there and multiply those together? And now, looky there. Shouldn't these two things be equal? And so then we solve that. Subtract the x. And wait a minute, we did this already, right? We're going to get 3.